Math 2414, sequences, video 7, continuity and convergence. The following theorem I think is super intuitive because you would probably do it even if I didn't tell you, by the way, this is something you can do. And it goes something like this. Suppose that we have a sequence, an, that converges to L, and we have a function that's continuous and defined for all values of an and for L. Translation. We got a pattern that converges to a number L, and our function can take in any number in the pattern as well as the thing it converges to. Then the conclusion that we can draw is that this new sequence, f of an, converges to f of L. This might look a little bit easier if it were written using subscripts instead of the function notation for an. This basically says if an converges to L, then f of an, the new sequence we would get by sticking each term of the original sequence into our continuous function, converges to f of L. What's really being said here, and this is at the core of continuity, is that when you take a limit of a continuous function, you can slide the limit inside the function. In other words, we're saying that if the limit as n approaches infinity for an is equal to L, then the limit as n approaches infinity of f of an, because the function is continuous, we can move the limit inside the function. That's the gist of continuity. Limits can go inside continuous functions, but we already said at the beginning that this limit is equal to L, so we can replace the inside of that with L. And that's all it's saying. So how does this look in practice? Well, let's take a look at a couple of examples. For the first one, we're going to take the sequence an equals the tangent of 2 pi n over 8n plus 1. Now, right out the gate, we have an issue with continuity because if a function is continuous, then its graph can be drawn in one continuous motion without lifting your pen or pencil from the paper. However, you should know that the graph of tangent is loaded with asymptotes. Specifically, at pi over 2 and negative pi over 2, there are 2 vertical asymptotes for tangent, with the branch increasing through the origin in between. And at every other multiple of pi over 2, or more descriptively, every odd multiple of pi over 2, 1 pi over 2, 3 pi over 2, next one would be 5 pi over 2, vertical asymptote, same branch in between, hitting the x-axis in the middle. And it's same thing backwards if we go to negative 3 pi over 2, branch in the middle. So this function automatically has an infinite number of discontinuities at odd multiples of pi over 2. So technically speaking, we have to make sure that our sequence is not going to stop at any of those points. Otherwise, we cannot get a correct conclusion. We could get an incorrect conclusion, I should say. So will this function hit any of those asymptotes? In other words, odd multiples of pi over 2. Well, if we look at the inside of this function real quick, 2 pi n, let's put the n, 2n pi over 8n plus 1. The number in parentheses is always even, provided that n is an integer or a whole number, because it's divisible by 2. And the number on the bottom is always odd, because it's an even number. 8 times an integer is even, plus 1 makes it odd. So whatever we put in for n, we're going to get an even number over an odd number with a pi after it. Can that ever reduce to an odd multiple of pi over 2? And the answer is no. Because if the number on the bottom is odd, it is by definition not divisible by 2. And so when it reduces, there's no way it can reduce down to just 2, much less an odd number over 2. Don't get me wrong, an even number can reduce to an odd number. If we had something like 20 over, we had something like 15 over 20, no, that's not good. We had something like 30 over 28, then the top is an even number, but when you reduce it, it would be 15. But an odd number can never reduce to an even number because an odd number is not divisible by 2 by definition, and reducing it down wouldn't suddenly make it 2. So by the structure of this argument of the tangent function, being an even number in front of pi on top and an odd number on the bottom, there's no way it could reduce to some odd number over 2. So there's no way the inside could be the location of the vertical asymptote. Now, if you totally did not even think that and just jumped right into what happened next, you would probably be okay. But in upper level math classes, you have to be aware of all the criteria in the hypothesis theorem. Specifically, when this one says f is continuous everywhere on the sequence, then it means, all right, so what is this limit? Well, if we take the limit as n approaches infinity of tangent of 2 pi n over 8n plus 1, because tangent is continuous everywhere it needs to be, namely everywhere that this sequence is defined, then we can move the limit inside. That's essentially what it means for a function to be continuous. If you have a limit in front, you can move the limit inside. And then you have a variety of ways of figuring out this limit. You could use L'Hopital's rule. Polynomial over a polynomial, both of them go to infinity. Take the derivative of both sides again. You could multiply both sides of this by 1 over n. Because if you did, you would get 2 pi on top, 8 plus 1 over n on the bottom, and as the n goes to infinity, this goes to 0, and everything that's left over is your limit. But you really need to know at this stage that if you're taking the limit of a rational function, one polynomial over another, and they have the same degree, in this case of both first degree polynomials, then that limit is just the ratio of their leading coefficients. So no matter how you approach the limit on the inside is going to be 2 pi over 8. Reduces to pi over 4. Which is continuous at pi over 4 because that's not the location of an asymptote. And you should know the tangent of pi over 4 is equal to 1. And if you're asking me why, you need to sit down and review your trig. And if you're still asking me why, me and you need to have talk. All right, so that's all the theorem says, is that if you're taking the limit of a sequence to find what it converges to, and you've got something inside of a continuous function, you can slide the limit inside the function, and then go from there. Let's take a look at another, a little bit stealthier example, but it illustrates an important move it's good to have in your skills. We have an equals n squared over the square root of n cubed plus 4n. Now in this one, we have a function of a function on the bottom. We have the square root of something on the bottom, but not on the top. So when we set up this limit, can we just put it on the top of the fraction and inside the square root? Yes, we can. But the problem with that is that we'll get infinity on both sides, which might make you think L'Hopital's rule. But trust me, if you try doing L'Hopital's rule on this, you would get stuck in an infinite loop. Anytime you try doing L'Hopital's rule when you have a radical, that power will never disappear. It's a fraction, subtracting 1 from it, it will always stay a fraction, or a non-integer, I should say. So what's the trick I'm alluding to? The trick here is to make the term of the sequence a single square root, because right now it's a square root in the bottom of the fraction. How do you make something a square root that is not a square root? That's easy. As long as it's not negative, and n squared is never negative for real numbers, you can put something into a square root by simultaneously squaring it and square rooting it. Because the square and the square root would cancel. Now this guy under here. So that would give us the limit n approaches infinity of the square root of n to the 4th over the square root of n cubed plus 4n. And now that we have a ratio of square roots, we can actually combine them into a single square root. Again, what I'm trying to accomplish here is to have something inside of a continuous function. And now I've got something inside a square root. Not just part of it, but all of it. With enough practice, and it doesn't take that, you can get from here to here instantly. all you have to do is square the part that's not under the square root and then park everything under a square root. Folks. All right, I had to take care of an issue with another online class. How appropriate. So anyway, we were taking the limit of this fraction, which had a square root in the bottom, and we were going to move the limit inside the square root by tricking out the whole fraction so it's under a square root. And I believe I'd already mentioned that it doesn't take much practice to be able to take something like that fraction and rewrite it as a single square root. And as a consequence, check for continuity, square roots are continuous as long as the inside is positive. Or rather, I should say non-negative. But since we're approaching infinity and presumably starting with 1, and everything in here is positive, we don't have any issues. You can slide the limit under the square root. Then go from there. And now notice that if we just analyze this by itself, we can park its result under the square root, and that's something you can do locally. Although you can also bypass L'Hopital's rule, because another limit you should know about rational functions is if you take a limit of two polynomials, one polynomial on top of another, take the limit of the ratio of two polynomials, one polynomial on top of another. If the degrees match like they did here, then that limit is just the ratio of their leading coefficients, which is 2 pi over 8. But if the degree on the top is larger than the degree on the bottom, that limit is infinite, because the top of the fraction is growing at a faster rate than the bottom. Complete the trifecta. If the degree in the denominator was larger than the degree in the numerator, then the limit would be 0. But in this case, the limit of the thing inside the red box is infinity. Therefore, an approaches square root of infinity, and I really hate writing that because it's not a well-defined expression. But infinity is so large that when you square root it, you still get infinity. Now, just for kicks, what would have happened if the n cubed had been an n to the 4th? Or even better, and I wasn't planning on tweaking this problem, but I want to make sure that you see a few variations. But what would happen if not only the n to the 3rd was the n to the 4th, and by the way, this is the last example, wrapping up soon, but the n squared on top had a 5. What if it were that? I challenge you to pause the video and see if you can replicate what we did before. I'll try to fix this. But pretty much we're going to do the same thing. We're going to trick out the numerator so it moves under a square root. And we're going to merge it all together, slide the limit inside, and take the limit there. I invite you to pause and try it, but I'm going to answer it in 3, 2. Let's start by seeing how efficiently we can merge all this into one big square root. The denominator already lives under a square root, so there's nothing to fix there. But to put something inside a square root that's not inside of a square root, you simply square it, and then it can live under the square root. 5 squared is 25. N squared squared is n to the 4th. Again, that move can become automatic with just a little bit of practice. You write that. Now we can slide the limit inside the square root because the square root is still continuous over this range of n values. And we can talk about taking the limit as n approaches infinity of 25 n to the 4th over n to the 4th plus 4n. But using the rule that we just alluded to, if the degrees match, when you're taking the limit of a rational function, degrees do match, or both 4th degree now, then the limit is just the ratio of the leading coefficients. The n to the 4th on the bottom has an applied coefficient of 1, which means the limit under the square root is 25 over 1, but that's just 25, and the square root of that is 5. So it's a nice trick to have in your arsenal to be able to take things not in the square root and make them inside of a square root by squaring them first. All right, so that's the end of this video.